All right, let's continue with our discussion of permutation groups. So 2 cycles are important, and we have a special name for them. We call them transpositions. Okay, there's that. Sn has how many? We have n choose 2 of them. Because that's how n choose 2 means precisely the number of ways of choosing 2 things from a set of n elements where the order doesn't matter. And the order does not matter because the transposition ij is the same as the transposition ji. Each one sends I to j and j to I. Okay, so there's that. A simple... Ooh, I hate doing that. When you start a new line with the word that you're defining, because then you have to underline it, and it looks really bad, in my opinion. But anyways, so a transposition is called a simple transposition. So instead of saying a simple transposition is blah, 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 I just changed the wording. So that's a transposition is simple if, and it is if it is of the form I plus 1, where 1 is less than or equal to I is less than or equal to n minus 1. So here we have obviously n minus 1 of them. All right, so proposition, any permutation is a product of simple ones, simple permutations. And to prove this, I'm just going to write I'm going to make this a really short proof. A1 through AR equals A1, A2, and then all the way AR minus 2, AR minus 1 times AR minus 1, AR. Okay, and why is this a sufficient proof? Well, we know that any permutation can be written as a product of disjoint cycles, and so if any permutation, or if any cycle, if any R cycle is a product of simple transpositions, then so is any permutation, because you just take each of the disjoint cycles and break those up into transpositions, simple transpositions. And basically from here you just have to check that this works. You could actually, I think I was able, like I had this as an exercise in a previous class, and this is one that you could actually come up with this permutation on your own. You know that, okay, if you want to write this as permutations, you need to send 1 to 2, 2 to 3, 3 to 4, A1 to A2, A2 to A3, and so on. And so you know which transpositions you need to use, you just got to figure out the order. So let's make sure that this makes sense. So let's say we've got some I, which is between 1 and R minus 1. Then we want it to go to AI plus 1. So what we do is we start at the right. Remember, these are permutations. We have to start at the right and move left. And we look for where AI appears. And if we look at the way this is written, AI is going to appear, the first time AI appears is going to be in the permutation AI plus 1. Because what this is going to look like is you have A1, A2, A2, A3, and so on, and then eventually you're going to get to AI minus 1 AI, followed by AI plus 1. So you'll run into the AI plus 1 first. You'll run into the transposition the simple transposition containing AI plus 1 first. And when you get there, it will send that guy to, well, when you get to the one with the AI plus 1, then the thing you're plugging in is AI. And so AI, when you plug it into AI plus 1, it will send it to AI plus 1. But then, okay, so after that, you have to look at the rest of the permutations that, or the transpositions that appear here. And the remainder here, let's actually write that out. So we've got A1, A2, AI minus 1, AI, got AI, AI plus 1, AR minus 1, AR. So you send in AI. The first transposition that contains AI is this one, and AI will be sent to AI plus 1. Then you bring this along and you send it through here. But if you look at all these transpositions, the highest index that appears in any of these is AI, which is less than AI plus 1. So AI plus 1 does not appear in any of these. And so AI plus 1 just goes right through and it doesn't change anymore. And so AI indeed goes to AI plus 1. Now what happens to, okay, so if we have I between 1 and R minus 1, then these two agree on where they send AI. What about AR? Well, this one, we can just look at it and you can see, okay, so AR immediately, this is going to send AR to AR minus 1, and then this is going to send AR to minus 1 to AR minus 2, and then it's going to get changed for every single thing here. It's going to go down 1 until you get to A1, which is that. So we're good. Okay. What else do we have? Now, one thing that's you might want to note, so you can write any permutation like this. Sort of the automatic mathematician thing to think is this unique? The answer is no. It's not how that parenthesis should go. And here's a counterexample. Okay, so where do all of these, so these all involve 1, 2, and 3. Let's see where they go. Here 1 goes to 3. Here 1 goes to 2, 2 goes to 3, and then it stays there, so 1 goes to 3. Here 1 goes to 2, and here 2 goes to 3. So all of these send 1 to 3. So here 3 goes to 1. Here, if you start with 3, this will send it to 2, this will send it to 1, so it'll go to 1. Here 3 goes to 2, 2 goes to 1, and 1 stays there. So they all send 3 to 1. Where do they send 2? This fixes 2. Here we have 2 goes to 1, and then 1 goes to 2, so it fixes 2. Here 2 goes to 3, and then 3 goes to 2, and so it fixes 2. So these are all the same. But these are different ways of writing it. So we don't have any uniqueness. All right, definition. Given sigma and Sn, if sigma is sigma 1, or through sigma L, where each sigma I is is a cycle, or isn't here, we'll call it an Ri cycle, then n sigma is the sum from j equals 1 up to L of Ri, nope. Here, let's just use j's here, or i's there. Ri minus 1. And so n of sigma here, this is what we're defining. This is going to be sort of the length of this permutation in some sense. Because, well, it's really the number of ways that you can write, or if you write sigma using transpositions the way that we did up here, then you will have n sigma transpositions in there. That's because if you look at this computation, here we have r indices, and here if we look at, let's see here, these transpositions are numbered by the first one, and so there's r minus 1 of them. And so an R cycle can be written using r minus 1 transpositions. And so that's why we define n of sigma to be, and of course these are disjoint, so that's why we define sigma to be the sum of the Ri minus 1s. Okay, so that's that. And then we have a theorem.